Force is essentially a push or a pull on an object, and it has both a strength and a direction, which we represent using vectors shown as arrows. When several forces act on an object at the same time, they combine into one overall force called the net force. This net force is found by adding up all the individual forces acting on the object. The important point is that it's this single net force, not each separate push or pull, that determines how the object's motion will change. For example, if you imagine a box being pushed from one side while being pulled by a rope on the other, the net force is the sum of those forces, which ultimately decides whether and how the box moves. Here we see the first law of motion illustrated with a soccer ball. When the ball is resting on the ground, it stays still unless something, like a push or kick, causes it to move. Similarly, when the ball is already rolling, it will keep moving in the same direction with the same speed unless a force, such as friction or someone stopping it, acts on it. This law helps us understand that objects do not change their state of motion on their own. Some force must be involved to start, stop, or change their movement. Inertia is the natural tendency of an object to keep doing exactly what it is already doing, whether that means staying still or continuing to move. There are three types to understand. First, inertia of rest means that an object at rest, like a book on a table, won't move unless something pushes it. Second, inertia of motion refers to an object in motion, such as a rolling ball, which keeps moving unless something slows it down. Lastly, inertia of direction means that when an object is moving, it tends to keep moving in the same direction. For example, when a car turns quickly, you might feel yourself leaning sideways because your body wants to keep moving straight. These three types help explain how inertia affects objects in everyday life. Here, the car is moving at a constant speed because the forces acting on it are balanced. The driving force pushing the car forward is exactly matched by the resistive forces, like friction and air resistance, pushing backward. Since these forces cancel each other out, the overall or resultant force is zero. This means the car doesn't speed up or slow down, but keeps moving steadily at the same velocity. Here we see Newton's second law in its most familiar form. The sum of forces equals mass times acceleration. This means that how much an object accelerates depends on the total force applied to it and its mass. On the left, the definition reminds us that acceleration increases with more force and decreases with more mass, and that force is measured in newtons, which combines mass and acceleration units. On the right, we revisit the concept of momentum, which Newton initially used to express his law. Momentum is mass times velocity, and force can also be understood as how quickly that momentum changes over time. This perspective is especially useful because it works even when an object's mass isn't constant, like a rocket losing fuel as it flies. The image with the tennis racket hitting the ball illustrates how force causes a change in motion. Here, the ball speeds up when struck, demonstrating acceleration as a result of applied force. Here, we see how mass and weight differ depending on location. Mass is the amount of matter in an object, and it stays the same no matter where you are, whether on Earth or the Moon. Weight, on the other hand, is the force gravity exerts on that mass. On Earth, gravity is stronger, so the weight is higher. On the Moon, gravity is weaker, so the same object weighs less even though its mass hasn't changed. Weight is calculated by multiplying mass by the acceleration due to gravity, which varies from place to place. This means gravity affects weight, but not the object's inertia or mass. When creating a free body diagram, the first step is to isolate the object by representing it as a single point in space, which simplifies the analysis. Next, focus only on the external forces acting on the object, like normal force, friction, applied force, and weight, and draw these forces as arrows originating from that point. It's important to avoid drawing the net force or acceleration as arrows on this diagram because they are results of the forces, not forces themselves. This approach helps keep the diagram clear and focused on the actual forces influencing the object. Let's review a problem involving a sprinter named Andrea, who weighs 63.0 kilograms and is accelerating forward at 4.20 meters per second squared. Our goal is to find the net external force acting on her. The first step is to identify the forces involved. Vertically, the normal force and her weight cancel each other out, so the vertical forces balance perfectly. This means we only need to focus on the horizontal forces. Next, we apply Newton's second law, which tells us that the net force is mass times acceleration. Multiplying Andrea's mass by her acceleration, we get a net force of 264.6 newtons acting forward. This force is what causes her to accelerate the way she does. Let's revisit Newton's third law, which tells us about the forces between two interacting bodies. When body A applies a force on body B simultaneously applies a force back on body A. These two forces are equal in size but push in opposite directions. This means that for every force we exert, there's always a matching force pushing back. This principle is fundamental to understanding how objects move and interact with one another. When a swimmer pushes against the wall, there are two forces involved that always come as a pair. The swimmer exerts a force on the concrete wall with their feet, and at the same time, the wall pushes back against the swimmer's feet with an equal force in the opposite direction. This example shows that one body cannot apply a force without experiencing a force back. The force the swimmer applies and the force the wall applies back are always equal and opposite, demonstrating that forces occur in pairs as a fundamental principle. This slide introduces the cancellation paradox, which questions the idea that every action has an equal and opposite reaction, a core principle in physics. The myth suggests that since forces always come in pairs that balance each other out exactly, they should cancel out entirely, resulting in no motion or acceleration at all. However, the paradox challenges this by asking, if forces perfectly balance, how is it possible for anything in the universe to move or change speed? This points to a deeper inquiry about how forces interact and how motion actually occurs, despite the seeming contradiction in the idea of forces canceling out completely. Next, let's look at a common misconception about how rockets work, known as the propulsion fallacy. Many people believe that rockets push off the ground or the atmosphere below them to lift off. But this idea doesn't hold up when you think about space, where there's no air or ground to push against. If a rocket needed something solid or a thick atmosphere to propel itself, it wouldn't be able to move once it's beyond Earth's atmosphere, in the vacuum of space. This problem highlights why the common explanation isn't accurate and sets the stage for understanding the real principles behind rocket propulsion. Let's take a closer look at how rockets move by pushing against the exhaust gases they expel. Essentially, the rocket engine applies a strong backward force on the hot gas molecules inside the chamber. In response, those gases push forward with an equal and opposite force against the rocket. Because the rocket and its gases form an isolated system, this forward force results in what we call thrust. The important takeaway is that the rocket doesn't need air or any external medium to move. It simply pushes against its own exhaust, allowing it to propel forward even in the vacuum of space. Now let's take a moment to understand how the simple act of walking demonstrates Newton's third law. When you take a step, you push backward and downward against the ground with your foot. This is the action force. In response, the Earth pushes back with an equal force in the opposite direction, forward and upward against your foot. This reaction force is what actually propels your body forward. So every step you take is a clear example of action and reaction forces working together, allowing you to move effortlessly. Let's now look at a problem involving forces and motion. A physics professor, weighing 65 kilograms, pushes a cart that carries 19 kilograms of demonstration equipment, including 12 kilograms for the cart itself and 7 kilograms for the equipment. She applies a backward force of 150 newtons against the floor, but there is also friction of 24 newtons working against the cart's forward motion. Our objectives are to determine the overall acceleration of the entire system and then find the internal force that exists between the professor's hands and the cart. This will help us understand how forces interact in real-world scenarios and how to break down complex motions into simpler parts to analyze the forces involved. Now, let's look at how to define the global system for determining overall acceleration. In this case, we combine the professor and the cart with its equipment into one single entity. The professor's mass is 65 kilograms, and when we add the cart weighing 12 kilograms plus the 7 kilograms of equipment, the total mass for the cart and equipment comes to 19 kilograms. Adding these together, the total system mass is 84 kilograms. By treating all these components as one unit, we can simplify the problem and focus on how this combined mass moves and accelerates. Now, let's focus on identifying the external forces acting on the system. Here, the professor pushes backward on the floor with a force of 150 newtons. According to Newton's third law, this causes the floor to push forward on the cart and equipment with an equal force of 150 newtons. At the same time, there is an opposing frictional force of 24 newtons working against this motion. When we combine these forces, the net external force applied to the system is 126 newtons in the forward direction. This step helps us understand the balance of forces that determines how the cart moves. Now, using the net external force we found, which is 126 newtons, and the total mass of the system, 84 kilograms, including the person, the cart, and the equipment, we apply Newton's second law. By dividing the net force by the total mass, we get the acceleration of the entire system. Doing the math, 126 newtons divided by 84 kilograms gives us an acceleration of 1.5 meters per second squared. This means the whole system, everything moving together, accelerates forward at 1.5 meters per second squared. Now that we have a clear understanding of the forces involved, the next step is to narrow our focus to just the cart and its equipment. By defining the system boundary around the cart alone, the force the professor applies is no longer considered internal, but external to this system. This shift in perspective allows us to analyze the specific push that moves the cart. Given the cart's mass of 19 kilograms and its acceleration of 1.5 meters per second squared, we can calculate the exact force exerted by the professor, making the problem more manageable and precise. Now, to find the internal force exerted by the professor on the cart, we use Newton's second law focused just on the cart itself. The net force acting on the cart equals the professor's force minus the friction force, which is 24 newtons opposing the motion. By substituting in the known values, the mass of the cart is 19 kilograms and its acceleration is 1.5 meters per second squared. Multiplying these gives 28.5 newtons for the net force, which equals the professor's force minus the friction. Adding the friction back over to the other side, we get the professor's force as 52.5 newtons, which rounds to 53 newtons. This calculation gives us a clear understanding of the force the professor must apply to overcome friction and accelerate the cart. To wrap up, remember that understanding motion comes down to three key ideas. Forces always come in pairs, meaning that whenever one object pushes or pulls, there's an equal and opposite force acting back. These forces affect different bodies, so they don't just cancel each other out. And the most important part is defining your system clearly. By choosing where you draw the boundary, you can distinguish internal forces from external ones, which makes analyzing complex motion much simpler and the math clearer. This basic framework is what helps us make sense of how things move in the real world.